Hello, everyone, and welcome to our Best Practices for Building a Cloud Data Pipeline webinar. My name is Jason, and I will be moderating today's webinar. Today we'll have around 30 minutes for our presentation, followed by about 10 minutes of Q&A. Before we jump into things, a couple of administrative items. First of all, we'd really want this to be a discussion, so we encourage everyone here to ask any questions you have in the chat panel. I'll be keeping track of everything for the Q&A session at the end. Secondly, if you want us to go over something again or repeat something you have missed, don't worry about it. We're recording this webinar and we'll send it around the recording via email afterwards. All right, so let's get started. I'm very happy to introduce Rami Amar, our co-founder and VP of R&D. He's been with Alooma since the beginning and has been obsessed with data for the last 15 years. In today's webinar, we'll go through the following things. So firstly, the introduction of why are we here, the basic architecture of a data pipeline, the challenges of building a modern cloud-native data pipeline, data architecture lessons learned while scaling the Alooma platform, lessons learned from the deployments at the New York Times and Publicis, and finally, summary and questions from you guys. So without further ado, I'd like to hand it over to Rami to get us started. Rami?
Yes, thank you, Jason, and thank you everybody for joining and listening in on the webinar. And without delaying, let's start. We're all here because we are data professionals, and what we're really interested in is changing our company's culture with data, and that means building dashboards and answering questions with research and making those answers accurate and on time. And what we're really doing most of our time is spending it on the pipeline, on getting the data from the different sources into our data warehouses in an organized and clean fashion. And I'm sure many of you already have experience with building such pipelines. They break on a daily basis and they leak events. They're very hard to change and improve. They're usually not very scalable. They're slow, and doing it right is difficult. It's really difficult. And before we dive into some of the advanced challenges and maybe the hidden challenges of building a data pipeline, let's first make sure we're all on the same page on what an architecture of a data pipeline looks like. And I guess you see this architecture diagram in front of you. It very much resembles our own architecture of our data engineering platform. When we set out to plan it, we started with the sources, and we kind of split the world into two. The sources that we have to fetch data from, whether it's documents from a MongoDB or records from a MySQL, or some third-party service that we need to pull data in from, anything from Google Analytics, AdWords, Salesforce, Marketo, and much, much more. That's one half of the world. And the other half of the data we wanted to fetch was from apps running on mobile devices or on people's browsers, or from other services that offer webhooks. And that half was integrations that receive data. So that's one part of the pipeline that brings in a lot of events into the transformation pipeline. And the first thing we always want to do is normalize all the different events into some uniform format that the rest of the pipeline can work with and not have to deal with different formats. And then the second step would be to fix and cleanse anything that didn't come in as we expected. Third step would be to enrich it with extra information, anything from currency rates to translate money values, to cities and countries to translate IP addresses, and even simple things like bring in the username if the user ID appears in a record. And the last thing we want to do before loading the data is the heavy lifting of splitting events, merging different fields, and maybe even doing some joins in real time. Once you do all your data transformations and data processing and crunching, before loading it to your data warehouse or whatever data destination you store your data in, you want to make sure the schemas on the destination are updated, whether you need to create a new table or add another column. You have to do that before you start converting your data to load it, and then you can make all your events, which we started by normalizing them into a uniform format. Now we'll have to translate it to the output format, copy it to some staging environment if necessary, not always necessary, and load it. This, I guess, three-phase process, it's amazing how the ETL acronym is still appropriate today. It's probably been invented somewhere in the 70s or 80s. And the only addition that we've seen to it, and it's been in the past maybe year or two, is transformations that happen after the data is loaded. Anything from consolidating change logs to vacuuming tables that have been cleared out or archived, to building more sophisticated tables of retention and cohorts. So now that we're all on the same page of what data pipeline that can kind of handle any type of source and any type of transformation, let's talk about the real interesting stuff. The main challenge of building all that is keeping your data's integrity. It's really, really difficult to make sure everything is accurate and keep what we call a 5-9 reliability standard. And we're going to talk about 3 challenges today. It's probably out of 7 or 8 big challenges that we listed when we prepared this webinar. The first challenge, we call it managing the dynamic world of schemas. The second challenge is how do you handle errors? Errors, we realized it very early on, is part of the data pipeline's life. You can't hope to not have errors. You have to plan on how to handle them as fast and as reliably as you can. And the third challenge we're going to talk about is the one that always surprises us with another edge case that we didn't think about. How do you make sure all your data is loaded once and only once? All right, let's start. Dynamic schemas, they always change. The changes can come from any part of your organization, whether it's from your own databases, either transactional, relational, with new tables and new columns being added every week, or your NoSQL databases that generally, I mean, that's their core. They don't have a schema, and every document can have a different schema than the one right before it. So from your data engineering teams to your developer teams that can add new features in the front end or in your apps, and then of course with every new feature you have to have more tracking events with more information about what the users are doing, to your backend developers that write logs and want to make sure their applications are performing as they expect and want to debug problems. I've never met an engineering organization that really keeps their logging standards under control, and that kind of data always comes in messy. And if that's not enough, then you have your marketing teams that run A/B tests on your websites on a weekly basis, and every month come in with a new marketing tool that they want to use and bring in the data to analyze. And even the least tech-savvy people, your sales organization, can make some changes in their sales process, update how their sales force works, and then again, your schema breaks. So this is something we also thought about when we started designing our pipeline. And the solution which we started with, which I have to say today, I mean, we've long ago understood it was a partial solution. We built out a schema repository. What you see in the screenshot is, we call our schema repository the mapper. It'll show you the different schemas that we see in the pipeline, and each schema, the structure of it, and some aggregated information on the data inside the schema. uh, we built what we call the automapper. We automated a process that sees the changes in schemas, modifies the schema on the data warehouse, and then updates the mappings between the source schemas and the data warehouse schemas. And the way the schema detection worked was by sampling the values that we see in the pipeline and guessing the data types of each value. That worked about 85, sometimes even 90% well, but that 10% of mistakes, those are very bad mistakes. They have a very high cost of understanding that you made a wrong mapping, because you don't realize it until you build queries on your data and you see that those queries are skewed, and all of a sudden you see one column out of 40, 50, sometimes even 200 or 300 columns, one column that's not how you expected it, and it fails your query. So it's not only hard to detect, it's also pretty hard to fix. You have to modify a whole table that's already loaded. Sometimes it's impossible, like Redshift doesn't support altering columns, altering column types, and restreaming, reprocessing all of your data can either take a long time or maybe sometimes really not possible. And the types of the mistakes we made were often really silly. Like one edge case that we had, we tried to guess when a timestamp would come in as integer or float, denoting seconds or milliseconds from the epoch. So they're integers. What you would guess is that they're integers, but we wanted to bring some more sophisticated logic, so we try to categorize integer fields that their values could be translated to timestamps in the past 10 or 15 years. That seemed to us like, okay, if valid timestamps are in the data, then we'll categorize that as a timestamp. Well, like I said, it worked 85% of the times. 10, 15% of the times, timestamp values come in as 0. And it's just a wrong timestamp, a wrong value. It doesn't mean that this type is not a timestamp, but an integer. So, and this is just one example of many, and maybe I'll repeat a few and tell a few more war stories as we go along in this presentation. So the more comprehensive solution we introduced was to get the schema from the source. It kind of makes sense. It's just a lot of work. We had to go through all of our integrations and add a function to their interface called import schema. And every integration that sent an event to the pipeline put a schema ID on it, labeled it with what schema it originated from, and we updated our automapper to detect schema changes from the actual data, and then retrieve the schema ID and get the original schema, whether it's from the MySQL database or from Salesforce or from any other source that can supply a schema. The automapper would go and fetch it, update the schemas on the data warehouse, update the mappings, and no more mistakes. Wherever we had a schema to import, we now translated to what the data warehouses expected. But that introduced another challenge, a challenge of translating types. Just for example, to explain what I'm talking about, if you ever tried extracting varchars from a MySQL database and loading them to Redshift, and you kind of try to translate the length of each varchar, then you might have noticed that you need to multiply the length by 4, because MySQL stores varchar lengths as characters, even though the data is in Unicode, and Redshift stores length in bytes. So these type of translations are endless, and they get even more difficult with the more inputs and outputs you support. And I guess our biggest customer that that took us to the next level of supporting multiple inputs and multiple outputs is the New York Times. When we started working with them, they had a wide selection of MySQL databases and wanted to load them to BigQuery. It really took us to the extreme of being able to support a lot of data types being translated to a lot of other data types on different data warehouses. And when we sat to design how we're going to solve that, we thought we're going to just have a huge translation matrix from a source type to a destination type. But it's a suboptimal solution. The reason for that is that it's a single place that's very hard to maintain and very hard to manage. And it also, it's just too many translations to hold in any configuration. So we wanted to distribute it and be able to manage type translations while developing an integration, whether for an input or for an output. And that brought us to design a uniform, all-inclusive schema. We call it the Alooma schema. And it basically can describe any schema from any integration that we have. And now it transferred the responsibility for translations closer to the data source or destination. And that makes it a lot easier and a lot more reasonable to maintain and fix bugs and update. So other than going back to what a data pipeline architecture looks like, when you get events into the pipeline, don't only normalize their format, try to also normalize their schema. It'll save you a lot of trouble when you continue expanding your pipeline. Let's go on to the next challenge. Like I said, errors are part of life. We encounter them on I would say daily basis, but it's really an hourly basis. And you can't avoid them. You have to expect them and find a way to deal with them fast. So I took statistics from our own system today, sampled about 1 billion events that have been stored aside as events that could not follow through all of the stages of the pipeline. And you can see the distribution. Most of the errors are usually value conversions, exactly relating to those integers that are actually timestamps that don't come in as the right value, or strings that come in instead of decimal numbers. Anything of that type falls under failed value conversions and strings to integers, overly long strings, any of that. But sometimes the data warehouse can issue an error, can run out of disk space, and all kinds of other weird stuff that we've seen. So errors are really part of life, and what we designed as a solution is to build a central sort of catch-all kind of buffer that any component in the pipeline can write events to it. And when writing events to it, we decided to write the original event and not how the event is mid-pipeline. It will allow to fix it and reprocess it through the whole pipeline and not develop interfaces to each point in the pipeline to be able to restream events. So that's very important. You kind of have to pay with memory, because as the event changes in the pipeline, you always carry along with it the original event, but it'll save you a lot of code in other parts of your system, and memory is a bit less expensive. So always store the original event, and if you really invest in this catch-all buffer, you should also build a querying interface to let you easily classify and group the events that failed together and help you prioritize what you're going to fix first. If you build such a buffer, there are some pitfalls that you should be aware of. The first one is getting events in a loop, because if they go into the error queue and then you make some sort of change that might split the event, it will be a problem running the event again and again through that splitting code. Or another pitfall is that if you're loading your events to multiple destinations, then failing one destination doesn't mean that it failed all of the destinations. And then if you have an event in your failure queue, in the buffer storing all the failures, and you resend them through the pipeline, you might get duplicates in one of your data stores. So that's another thing to watch out for. When we started our implementation, we used the Kafka queue. We still use it today to store all failed events with metadata on each one, describing why it failed, where in the pipeline it failed, and how many times it's been through the pipeline, exactly to avoid loops. We issued notifications every time events went to the error queue, and that helped us understand that there are events we need to take care of. And to be able to fix them quickly, we used a Redis server to store samples of them. If you're familiar with Kafka, it's great for serializing events and reading them sequentially. But if you just want to sample events randomly, it's not as performant. So we exchanged that with the Redis. Our next version, we built that querying interface that not only helps you prioritize what to fix first, it will also help you find the needles in the haystack. So we kind of replaced the Redis with Elasticsearch, and instead of sampling the events, we indexed all of the events. And then with Elasticsearch, we can easily build aggregations on, and you can see it in this screen. We can build aggregations on how many events failed from each input, how many events failed of each schema. We call schemas internally event types, and how many events failed for each type of error or each type of stage in the pipeline. And you can also see samples and really dig into that and choose which ones to fix. And the needle in a haystack analog, sometimes you can get hundreds of thousands in error and you don't really have the time to deal with them. But you have one event that's very important that you want to find and fix just that, because 1 out of the 100 tables you have in your MySQL that you're replicating to your data warehouse, it's a very important transaction that affects some important KPIs, and you want just that. So build a good restream queue. Third challenge, and like I said in the beginning, probably the one that surprises the most, because it's kind of hard to grasp where it's going to fail. We call it the exactly once paradigm. We also wrote a blog post about it a long time ago, and it has to do with how do you make sure all your events reach your destination, your data warehouse, once and only once. At least once. It's pretty straightforward. Actually, for this whole question, you can always refer to how TCP works with acknowledgement numbers and sequence numbers. So how does TCP guarantee at least once that all packets will reach at least once? It numbers every event and makes sure to receive an acknowledgement from the end of the pipeline that all the events have been received. The problem is that making sure they've been received only once is not that simple. Going back to the TCP analog, the receiving side keeps a sequence number, the number of events it has received, and that number always grows. So if any event comes in twice, it will come in with a number that's lower than the current number of events received. So it knows to skip that. In our case, it's a little bit more difficult to do that. And what TCP does, it's called the dictionary definition to idempotency. You can see it here. The concept of idempotency is simple in words. A duplicate event will overwrite itself when it reaches its destination. So it's easy with TCP when you have each event numbered, and the number always goes up. So the receiving side can look at what the last event it received was, whether it was 250, and if the next event it receives has a sequence number smaller than 250, then it will just ignore it. In practice with data pipelines, this is very difficult because you can't always number your events sequentially, and you do need to identify all your events somehow and make sure the identifier is unique. You can't always identify events by hashing their content, because two events can have the same content and they're not necessarily duplicates. They're just two identical records in table. That's a very plausible case. And if you generate an ID for events, then it really matters when you generated that ID. And I'll describe how we do it in a minute. Another difficulty that you can come across while trying to make your pipeline idempotent is that not all data destinations will support overwriting of existing events. Redshift doesn't. Redshift has a primary key constraints on its tables, but it doesn't enforce them. So effectively, you can load identical events that a normal relational database would reject. Redshift will just accept them as is, and not only it will accept them, it will probably break some queries that will run on the table. A different example that if you refer to S3 as a data warehouse, then S3 can be idempotent. If you label your data with file names, then loading the same file name to S3 will just overwrite the last file name. So that's another challenge you have to do and you have to deal with. And the real difficulty and the real surprises come in when different components of the pipeline fail. The pipeline is a pipeline, and every step of the way holds a certain number of events. If you want to stop one of those components, or maybe it fails due to a bug or due to maintenance or any type of reason that components fail, and they always fail, it's also something you have to live with, then the next time it comes up, it will probably try to resend the last few events it transmitted before shutting down. So either you implement idempotency each step of the way, or you implement it end, but it's all very, very difficult, and that's why I said it keeps surprising us with different bugs in different parts of our pipeline. So it'll be very difficult for me to describe our solution end to end, but with I guess the two main things we had to do to make sure all of our events pass our pipeline at least once is give them IDs for every event and for every batch of events as early as possible. If we can get the ID from the data source, like a primary key in a transactional database, or a collection and document ID on a MongoDB, or even our SDKs, we generate the ID when the track function is called. So as early as possible, we generate an ID, and that allows us to correlate events on the data warehouse on the end of the pipeline to the beginning of the pipeline, and that really is kind of a safety net for any kind of duplicate that can be generated mid-pipeline. Being able to recognize duplicates at the very end of it is probably the best thing you can do. The problem with Redshift, like I mentioned, is that it's not idempotent. Its primary key constraints are not verified, so overwriting data is not an option. What we had to do is keep track of which batches we loaded in a separate table, and if you happen to be an Alooma user, then you've probably noticed that all the table Alooma loads to has another shadow table with an underscore meta to it, suffix to it. So whenever we load data to a table, we make sure the batch is loaded and recorded in the meta table in an atomic transaction, in a single transaction. And before loading a new batch, we check the meta table to make sure we haven't already loaded it. So that's how we implement idempotency in our pipeline. And it's really difficult. With every step and every data destination, a different solution has to be kind of designed. And that brings us to the end of this webinar or this presentation. I hope I explained a little bit why 5.9 integrity standards require thorough design and battle-tested implementation. And when you plan your next data pipeline, try to summarize to 3 major points. Build a schema repository and automated tasks that run mapping. Integrate your sources end-to-end with idempotency in mind, and build some sort of catch-all error queue to help you collect everything that falls off from the pipeline and fix it. Hopefully we have, I told you, we listed about 3, we talked today about 3 challenges out of about 7 or 8, and we maybe run another webinar or talk about them in our blog. How to build integrations in the easiest, fastest, and most reliable way. And integrations, that's a whole nother world of edge cases and APIs and things to be prepared for. We will talk about embedding customizability, dynamic customizability, so so you can easily fix all the events that don't follow through correctly through the pipeline. We haven't talked about flow control and back pressure and using buffers and backups in the pipeline, which is probably the most painful failures we had were due to bottlenecks and insufficient buffers. And the last challenge that we can talk about in the future is how to make your pipeline scale. Lots of barriers, very hard to partition your pipeline and make it run on a cluster.
All right, great. Thanks a lot, Rami, for that. So everyone on the line, if you haven't already, please post some of your questions in the chat panel that you see there. It looks like we've got a few questions actually that have rolled in already. So Rami, I'll just mention some of them. So the first question is, how does your solution to the only once problem handle when the data in the warehouse legitimately needs to change?
Okay, so if I understand the question correctly, when I look at the idempotency challenge and the exactly once challenge, I look at it as being kind of finished when the data is in the data warehouse. And from there, if you run, I would have to understand an actual use case to answer that. Okay, unless if you have queries that run on your database and generate new data or copy the data inside your database, is this what the question is about?
I think so, but I think we can get more information about that question later and follow up with the person individually. So we'll move on to the second question now. So the question starts off with, for example, if I'm storing a timesheet data in Redshift for when an employee logged time and they made a mistake and I need to fix it in the warehouse, how does Alooma or how does the Alooma solution handle this?
So it's a good question. If the error was during loading, for example, the timestamp we're supposed to have a time zone but didn't, and now a time zone has to be added, then two options you can have with Alooma. You can reload the data if it's not a large amount and just fix it. It'll take you a few minutes. Another option is to use a new feature we're just rolling out to alter a column's type, and if that falls under a type conversion, then it'll be fixed that way. If it's just several records that you want to modify, your best chance is to run a query and modify it.
Okay, great. Next question is, can you explain a bit more on how you would change the field type in the database, for example, from an int to a float? They followed up with saying, I thought that's not often easy to do directly.
True. It's what you have to do is create a new column of a float type, copy all of the data from the integer column to the float column, and then drop the old column. It will not bring back the precision from the values that have already been loaded, but going forward, any new value will now be a float, and you won't have an inconsistent table with two columns having split values.
Okay, great. Next question is, going back to the schema normalization solution, who makes the schema changes and how do you monitor when they change?
Good question. The schema, the entity responsible for changing the schema is usually external to the data pipeline. It's somewhere in the source. And the way we recognize the schema change is by using the schema repository. We have one component in the pipeline that it's sort of a classifier and schema detector. With every event that passes it, it will extract its structure and update the schema repository. The schema repository, it not only holds the structure of the schema, it also holds the mapping of the source schema to the destination schema, to the schema in the data warehouse. And when the schema is updated by that classifying component, if there's a mapping mismatch, we recognize that as an updated schema, a schema that has been changed and needs a new mapping.
Very good. Next question is, what's the best way to enforce star schema architecture in the data warehouse, for example, in Redshift?
That's a good question. I mean, enforcement is usually dependent on human policy. With Alooma, what you would first let's start with what a star schema is. Usually, a star schema relies on one table that has all of the facts, all of the raw facts, and a bunch of other tables that have extra information that can enrich the fact table. It's okay with Redshift, but I think, well, if we talk about Redshift, running queries with joins is not the most performant type of queries. So if you can denormalize your star schema into one huge fact table that has all the data with as much columns as you need, that will usually run queries faster. Now you can do both with Alooma because every type of event, whether it's a fact record or whether it's an enriching information to that fact, it will have a different schema, and you can choose to which table to load that schema. And then, like I said in the beginning, it's your own policy, however you want to map it. Our automapper will just be naive, and every schema it sees, it will create a table for it and load the data to it. If you want to change that, then you just take it off autopilot and map it yourself.
Awesome. So that's all we have time for today. On behalf of Rami and the Alooma team, we'd like to thank everyone on the line for joining us today. We hope you enjoyed the discussion as much as we did, and we're looking forward So look forward to the recording of the presentation in your email, and stay tuned for future Alooma webinars. Have a great day, everyone. Bye.